Before we get started, I wanted to fill in a couple more slots just so we feel we've been making progress. It's an illusion, but we did do a couple of things last time. We talked about the S2 cross T2 slot last time. We called it Yang-Mills-Higgs theory. And what we said is that S2 cross T2 theory on the circle attached class functions on the group. So we talked about the compact case and the complex case, but let me just write. I'll just write class functions on the group. And then we also talked about some kind of invariant that you might attach to a Riemann surface in these Yang-Mills theory. We said it doesn't really necessarily make sense as a number. Maybe it makes sense only relatively, but in the finite group case, it was trying to count the number of local systems for the finite group on a Riemann surface. In the compact case, it was some kind of volume of the space of local flat connections. In the complex case, it's also trying to be that whatever, doesn't make much sense, but let's just write this anyway. This is the volume of the space of local systems. So I'm writing here, you can't read it, but trust me, I'm writing something like that. Volume of the space of local systems. So now we have a couple more slots, and just to feel even better, though we haven't justified it, Andy and Kevin both talked about something that I want to put here. Andy called it C cross S1, and he explained that that when you look at theory X on a Riemann surface across a circle, this was described as something that there was a sigma model into the Hitchin space of the Riemann surface sigma. Kevin gave us a name for the topological field theory associated to this, which is Rosansky-Witten theory. So I'm just going to write here RW Rosansky-Witten theory on the Hitchin space of sigma. So this is where the Rosansky-Witten theory will be. Okay, so that's we'll discuss what this theory actually is today. Kevin also told us another fact, which is if you take Rosansky-Witten theory and reduce it on a circle, you get the B model. So if you take sigma cross S1, that's sigma cross T2. I already wrote something.
Maybe that's the owner.
It's Michelle Yang, anyone? No? Okay. Sorry, Michelle. And so Rosansky-Witten theory reduced on a circle is supposed to give us the B model. So I'm going to write here under geometric Langlens, and we'll try to reconcile all of this. I'll write here B model on the Hitchin space of sigma. Okay. Anything else someone wants to fill in? Well, okay, let's leave it at that for now. We'll try to discuss some of these slots a little more, and the goal will be to fill in a lot more if we can. Okay. So, but before we do that, I wanted to spend some time. What I'd like to do is talk about Rosansky-Witten theory and the B model today. But before we do that, I wanted to introduce one of the main structures that has appeared in several talks. It's going to be kind of what is going to be the main star of a lot of what we're going to do is the notion of local operators. But I'm going to only work in the setting of topological field theory, not in supersymmetric field theory. So, what can you say in topological field theory? What should be a notion of a local operator? And so the idea is I have my space-time, and I have a point in space-time, and I want to make measurements of my fields at this point. So there's a natural thing that I could do is I could take a little ball around this point and cut it out. And I draw here a little, I have here a little n-1 sphere around this point. Now what is, so I want to propose that z of the n-1 sphere is going to be what we'll call local operators. Now, how should we think of this? Remember, I'm thinking of this it's topological, so I could choose the sphere to be as big as I want, but I really should be thinking about this as a very small sphere around this point. And if we, in our caricature of what the field theory assigns, this is functionals on fields on fields are on this n minus 1 sphere. So in other words, this link of a point. Now, how does this, what kind of functionals should you think of if I have fields? There's kind of two kinds that Tudor mentioned. You can think about order and disorder operators. Two examples. One kind of thing I can measure is I can look at fields that extend into the disk and measure something about their value at this point. So one kind of example would be fields that actually are defined on the interior disk. I can measure their value at this point. Another kind I could do is I can also look at fields that have a prescribed kind of singularity. My functional might be like the characteristic function of fields with a prescribed type of singularity at this point. So these are functionals on fields that are allowed to have any kind of singularity at this point they want, and I can do various kinds of measurements. And whether or not, the first one is called order, the second one is called disorder, but we're not going to distinguish any of them. We just have this single vector space of functionals on boundary values of points. And now, what can you do with this vector space? Well, let's draw a couple. So maybe one thing to point out here, well, okay, let's not point out anything yet. What can I do with this? Suppose, let me draw the picture a little differently. Suppose I have a compact manifold n. So here, if I have a compact n manifold and I have a point in the interior, then I get, so this gives me a map from z of Sn minus 1 to numbers. So given an element of z of Sn minus 1, I can decorate it here, and I get a number. And I can think of this number as being the path integral on the space of fields of M. I do my usual path integral, d phi, but I insert some operator and evaluate it at this particular point x, operator of phi. So here I have an element, I think of an operator at the point x. This is the point x. And so this is what I would call the expectation value of this operator at x. So that's one kind of picture. I can think of these as giving numbers. These are these expectation values. Sorry? Yeah, between friends sets. Okay, so that's a number I can get, which is my caricature for the partition function. Now, why are we calling them local operators? The kind of main example I want to think is, suppose I have a closed n minus 1 manifold, and I want to think of crossing it with time. So here's my closed n minus 1 manifold, and here's an interval of time. And now I can think of, suppose I have your favorite point, x in this manifold n. So let me draw this point at halftime. So here's point x times 1/2. 1/2 is not terribly important, right? Everything is going to be locally constant in my position, but let me just choose to call it 1/2. And I can remove a little sphere around this point. And what is this picture of? This is a picture of a cobordism from n minus 1 union and n minus 1 sphere to n minus 1. So it gives me a map. Let me write it the other way. So I have a map from the z of this n minus 1 sphere, tensor z of n. This is my vector space. This is my Hilbert space of the theory on n. I have a map to z of n. And so this is what I'll think of this operator. So given an element, this local operator, it defines an operator on z of n, okay, that depending on the choice of the point. So these are what I want to call them local operator. Now, one thing that's going to be useful to note here, we're being kind of loose about what kind of field theory you want. I've kind of pretending everything is oriented, but sometimes it's useful to remember framed manifolds. And when I think about this as framed manifolds, the n minus 1 sphere I have here is the blackboard framing. So I'm really thinking of this as having this kind of, think of a little annulus. This is my higher dimensional annulus with the kind of blackboard framing. So this is the annulus, it's not the cylinder. In one dimension, we drew in 2 dimensions, we drew 2 different pictures. There's this version of the cylinder, and then there's kind of this version of the cylinder. And they're different as framed 2 manifolds. So the one that appears here as local operators is really this one. Okay. So let's. So in fact, it's useful to connect this with pictures that you may know from geometric Langens or other representation theory. It's useful to think, since everything is, this is again similar to what Andre was doing in his talk, let's start collapsing stuff. So we would draw Andre's blue rays and start shrinking everything. Everything is kind of locally constant. So I could draw this picture in a kind of more extreme way, which is I can take my space n, take the space, and I'm going to just kind of double it. I really can't draw this very well, but I'm going to kind of try to double n around this point x. So I'm going to write n, I'm going to make a space which is just n union n glued over n minus the point x. This kind of non-Hausdorff space where I double this point. So that's kind of what I get if I think of this picture and kind of collapse this kind of irrelevant time direction. So what you can think of is that we have fields on this funny space, fields on n union n over n minus x. This is a correspondence from fields on n to fields on n.
Can you try one of the other markers?
I can try. Yeah, they're.
I can also go get another one.
I mean, I bought these yesterday, so I think it's just the board. Yeah. But yeah, let's try. So, can people read this so far? We're sort of. Okay. So we have this correspondence from field. No, that doesn't help. So fields on this double thing are a correspondence from fields on n to fields on n, which is just pairs of fields that are identified away from one point. And this operation that we're doing at is exactly what you might think of as a Hecke modification. You're taking fields and trying to modify them at one point, and that's what these local operators are doing. They're kind of functionals that you can insert in. So that's another picture. And again, that's really important here that we're thinking about this as a framing that it's kind of this framing. Let's call this cohomology framing. So that's another kind of caricature that's kind of more suitable for algebraic geometry for what these local operators are doing, if you don't like intervals. Okay, so let's just say one more structure about the local operators. So we said what they do on n manifolds. On n manifolds, they give us correlation functions. Just expectation values. On n minus 1 manifolds, they gave us these operators. What do they do on n minus 2 manifolds and below? They still do something. You could just keep drawing the same pictures over and over again. So let me try to draw something. I can't really draw this very well. So here's an n minus 2 manifold, and I'm going to cross it with R. So this is P n minus 2 cross R. So that's an n minus 1 manifold. And I can draw the same picture. I can cross it with time. And at a particular point, I fix my point. Now x, I want my x now to be in Pn minus 2. So again, I'm going to do at halftime. I draw this point x, and I'm going to remove a little ball around this point x. So again, I have this n minus 1 sphere. And what you get out of this is something we already did in the two-dimensional case, where the pictures looked less crazy. I guess I drew it this way, just to remind you of the picture I drew. I drew a picture like this, where you took the identity functor of some category, and you removed a little circle in time. And so what you get out of this is that z of Sn minus 1 gives you endomorphisms of the identity of whatever it is that you attached, identity functor, say, of z of Pn minus 2. So it acts on Pn minus 2 internally. And of course, there's nothing special here about Pn minus 2. Any picture you can write in the topological field theory, I can always remove little points and have these operators act. So the idea is that this entire field theory is linear, is a module over these local operators. Everything in set has this structure of local operators. Now, to make that useful, I need to say what kind of, when I say a module, I want to have an algebra. So far I've just had a single operator. What is the composition law? So there's a composition law on these spheres. Is this everyone? Make sense so far? So now I want to. So the point is that these are not just operators. This is an action of an algebra. So z of Sn minus 1 will be an algebra, and let's see what kind of algebra it is. So z of Sn minus 1 is an En algebra. So what is En algebra? It's a name for the structure carried by ZSN minus 1. So it's really, exactly. But it really is sort of exactly built for this story. So let's just draw the pictures when n equals 2. These are pictures we've seen several times. For n equals 2, the idea is that if I have, how do I compose? So I'm trying to do a composition law on the circle. And remember, I'm thinking of the circle as the annulus. It's a circle with a blackboard framing. So I can draw a circle, and I can draw another circle. And this gives me a coordinate from circle union circle to circle. So this gives me a multiplication. So I get a map from z Sn minus 1, tensor z Sn minus 1 to itself. And of course, you could draw this in higher dimensions, right? Just take a sphere and remove a couple, remove a couple of smaller balls. So you get a multiplication. But you don't get a single multiplication. You get a multiplication for every pair of for every such picture, for every pair of circles inside of the big circle. Okay. So you have a family of multiplication. So really, you have a family of such, family labeled by the topology of the space, by the space of such pictures. There's a space of such pictures. Now, when I say family labeled by, everything is topological. We said everything depends locally constantly on this. So what we wrote before is that we're supposed to have a map from chains on the space of pairs of pants. So really what we have is a map for each one of these guys. We have a product on z Sn minus 1. We have a multiplication. Now, this space of pairs of pants is not that complicated. Topologically, I just imagine that putting one of them at the origin, and then the other one has a sphere, can go any way around. So topologically, this space of pair of pants is just the n minus 1 sphere itself. Did I get the numbers right? N minus 1? Yeah, OK. So topologically, this space of pair of pants is homotopic to just the n minus 1 sphere. So the chains on this, there's kind of two chains. There's something in degree 0 and something in degree n minus 1. So now if I pretended that I didn't write chains, let me write homology for a second. Suppose I pass to the level of, pass to cohomology everywhere, so I don't ignore differentials. Then what do I have? I have two operations. Well, I'll call them dot, which is a degree 0 operation, coming just from the space is connected. There's one operation of degree 0, and there's another operation which I'll call bracket, which has degree n minus 1. Minus n minus 1. It's in homology. So I'm giving cohomological grading. This is a negative. Let me write. It's 1 minus n. OK. So I have two operations on the thing labeled by the n sphere, one of degree 0, one of degree n minus 1. Of course, to give an algebra, I need to be able to compose. This appeared in Andre's talk. Let me just remind you that this is what televisions call picture-in-picture composition. You write, if I want to compose this picture with some other picture, I just draw this picture in this picture. And then kind of remove the boundary. So there's a natural way of composing, of stacking such pictures together. They give you a bunch of operations. This can be formalized by the structure of an operad, and I won't go into that. But this is an example of, this is the En operad. So what that means is that these operations will have various relations between them. And one, I think this is Fred Cohen, I don't know, there's theorem that says that these two guys, that the relations of this structure, the full structure of relations are saying that these satisfy the relations of a Poisson algebra, but it's of degree, 1 minus n. In other words, this multiplication is commutative, and this multiplication is a Lie bracket of this degree, and moreover, it's a derivation of this product. It satisfies the Poisson relations, except that it's a graded version. So when n equals 2, this is called the Gerstenhaber algebra. OK, so that's what so the point is that the structure that I have on z Sn minus 1 is, there is a commutative multiplication, but there's also something else remembering this topology, which you won't see in a discrete setting. You'll see when you have enough room to see graded structures, there's something coming from moving a point around around another one, kind of a residue. If you've seen vertex algebras, it's exactly residue. Anyway, now I did something kind of uncool. I replaced chains by homology here, and there's this theorem, this Kontsevich formality. There's formality theorem says that I'm probably misstating like everything else, put it with quotation marks. That this this homology of En, which is what maybe I'll call it Pn. This is what I wrote here. This is Pn is equivalent to En. So in other words, there's a formality theorem saying there's no extra structure on the chain level over the cohomology level. Yeah.
So the statement that Z of Sn minus 1 is an En algebra, does it depend on whether the TFT is from a twisted version of a Lagrange?
No, absolutely not. I don't know what a twisted supersymmetric field theory is. That's the point of these talks. I'm trying to present things not knowing what it is. Just from a topological field theory, in the sense we described, you always get this En algebra. And using formality, you can pretend that you know what En algebra is. It's just Poisson algebra. You should be suspicious of this and use it sparingly. But that's the intuition. So we'll treat it. It's a kind of suspicious thing, but it's there. So we can say we know what an En algebra is, but we'll try not to use it too much. Yeah.
So is this for framed TF?
Right. So all the pictures I've drawn are framed. I'm going to always everything I've drawn. I can constantly keep this blackboard framing. So if I give you a frame topological field theory, I get this En algebra. If my field theory is actually oriented, which my examples all will be, then I have more structure because then I can rotate the sphere. This picture is not, the framing that I'm writing is not invariant under rotation. But if my theory is oriented, then there's an actual extra structure, which is this could be, this is N? SON equivariant. I can rotate this guy around. And this guy has a nicer name. This is called an n-disk algebra. So if the theory is oriented, you get something called an n-disk algebra, or in 2 dimensions, a BV algebra. Or a BV algebra, but different use of BV than in Kevin-Stock. But so if the theory is oriented, you get more structure, and we'll talk about that later, but you always get this En structure. So that's why it's useful to keep track of the framing, is keeping separating these two notions. Yeah.
Sorry, I just have a minus sign. So
Great.
It seems like the operation coming from the homology of Sn minus 1 should have to be N minus 1.
It's the homology. I mean, I'm probably off by a sign. But I think this is homological grading. So it's everything I'm thinking of is in cohomological grading, and so this is a negative. Yeah, we'll see this in a second. Well, not in a second. Probably the way we're going next week. But this comes up how this comes up naturally in Rosansky-Witten theory. But okay, so this is. So this is the structure. So and moreover, if you think about these pictures, all the pictures that I drew, like I gave you this manifold, and I did these operations on it with a sphere, you can start drawing a bunch of spheres together, and think of if I have a bunch of these local operators, I can think of putting them very close together. This is the operator product expansion, and replacing it just by a bigger sphere. This is all to say that this action I get, that Zn is a module over this En algebra. It's a module, left module for this En algebra. So this structure of En algebra is encompassing the OPE of fields. It's encompassing the algebraic structures, and everything that acting is acting as an algebra. So when I wrote something was endomorphisms of an identity, things like that, that was as an algebra. And this is the algebraic structure we have. So now so what I'd like to do is talk about this in some detail in these 2 examples, in the Rosansky-Witten theory and B model, what these structures are. But since we've talked about it in all of the talks yesterday, I think. Let's just revisit moduli space of vacua, and we'll revisit it again next time, kind of try to get more and more sophisticated in what we mean by that. But again, my naive take on the moduli space of vacua of Z, and again, this is not going to be the final answer. This is what we can do so far. Moduli space of vacua of Z, we decided what we're going to do is our naive take is going to be just take spec of Z of Sn minus 1. So what's the idea here? We realize that the entire field theory, all the operations, all the structures in the field theory are all linear over this ring. This acted on everything in sight. So that means that the entire field theory, in a sense that we will make precise hopefully later today, the entire field theory is linear over this ring. It lives over this spec. Now, what is this spec? Now, there's two definitions. Neither of them is going to be terribly satisfying, but let me give you two definitions. There's one definition this is the really stupid one, but it's the right one. You know, I'm just going to define an affine En scheme is En algebra's opposite. So an affine scheme is just a ring where you reverse all the arrows. Okay. So I know so this guy is an affine En scheme. That's what spec means. This equal is called spec. All right, so we know what an affine En scheme is. Now, this gives you no intuition, but it's formally the right thing. So a better thing to say is that, a suspicious thing to say is using formality. This thing is actually not that weird. We have, Z of Sn minus 1 is a commutative differential graded algebra. So spec of Z of Sn minus 1 is just, and I'll stop writing the word derived because it's supposed to have been everywhere. It's just an affine scheme. So I think of this guy with its commutative product. It is just a commutative ring. Okay, it's graded, or differential graded, so fine, but so ignore the word derived if you don't like it. So there's an ordinary scheme here, plus it has an operation which is a Poisson bracket on functions. So functions on the scheme carry an action of a Poisson bracket of this degree 1 minus n. And we're really only going to keep track, basically, if this Poisson bracket is even or odd. So there's really going to be only two cases from our point of view. There's when the bracket is. So for example, if you're E3, that means that this is an even bracket. And we'll just think of this as an ordinary Poisson scheme. Just an ordinary variety with a Poisson bracket on functions. If it's odd, then we really want to think of it as an odd thing. But I'll say this. We'll see this in more concreteness when we talk about Rosansky-Witten theory. So there's somehow only two kind of things. But basically, that's what our moduli space is. It's a Poisson space. And the claim is going to be that the reason holomorphic symplectic structure Poisson structures were appearing in the talks yesterday in the moduli space of the theory is coming from this. Okay? So that's why the moduli spaces of these n equals 4, d3, d equals 3 theories were having this Poisson structure. They'll come out of this operation. So that's what I'd like to explain. Yeah?
So I could imagine there's one other thing I could have tried to do, which was to take some sort of n center. I don't really mean.
That's right.
One, I know what the center of an algebra is.
Yes.
And that's also an important thing in non-commutative algebra.
Mm-hmm.
And that's not on your list yet?
It is. I mean, sorry, it's not. I mean, that's what this is. So if I think about, so the idea of this vague picture about endomorphisms of identity, I don't want to make this precise, but it's that the Z of Sn minus 1 is the whatever you might mean by the higher center, and I don't know if it's n or n minus how you would label it, but it's some higher center of Z of a point.
Sorry, so what I meant was that, like, Z of Sn is sort of an n algebra. It's not a kind of, I'm at the center of this n ring itself. I meant like the fully commutative center.
What does that mean?
I don't know. Well, I only know what it means when n is 1. When n is 1, I'm just doing quantum mechanics.
Yeah.
And Z of S0 is an associative algebra.
Yeah.
And one of the things that I might care about when I'm doing quantum mechanics is the center of that associative algebra.
That's right. But the claim is that centers are never commutative. It's kind of an illusion. right? I mean, the center of an associative algebra is not a commutative algebra, it's an E2 algebra. We'll see this in a second. But center, I mean, if you're in a completely discrete setting, then you might think the center is commutative because you're ignoring this bracket. But centers always have this right. It might happen to be 0, but that's rare. Centers have commutative. So we talk about Hochschild cohomology of an associative algebra. Hochschild cohomology of an associative algebra is an E2 algebra. Yeah.
Localize that affine scheme by invert some function of that affine scheme.
Yeah.
Do I get a field theory that's defined over the complement?
We'll have to. I think the answer is yes. You have to be careful. I mean, I don't know exactly what the localization theory for, this is sort of very mildly non-commutative geometry, so you have to be careful what you localize. I mean, I'll try to make precise in what sense this is a kind of a sheaf of theories over this space, but you have to be careful because it's not. I think you should not trust formality in these questions. You should really think of what an EN scheme is, and then to formulate what it means for our theory to live over this space, we'll need factorization homology. And so there is a precise notion of what it means, but it's not. So, but I don't know how to. Probably other people here know how to answer that, but I can't. I don't want to commit. Okay, so that's the structure we're going to. Yeah. So the idea is that this is some kind of higher center. So in the case, let's just do the two examples. So probably the rest of. I want to give. Oh. Okay. Thank you. Great. So I want to spell out some of these structures in the case of the B model in Rosansky-Witten theory. And again, if you don't like affine things, if you're bothered that examples of Hitchin spaces and so on are not affine, just hold on until next time. I mean, we're going to. It's not a problem of the theory. We'll give you something non-affine. This is just our first approximation. Okay, so let's start with the B model. So we have already written here sigma cross T2 was supposed to be the B model on the Hitchin space of sigma. So let's try to explain what the B model is. Yeah. Is this worse or is it equivalent? Okay. So what's a B model? And again, this appeared in Kevin's talks, mostly as through Rosansky-Witten theory. So if I give you M a variety, I can study. There's a two-dimensional supersymmetric sigma model, but I'm going to only think about a topological theory. But there's a two-dimensional sigma model into M. So what does sigma model into M means? It just means that my fields are going to be some kind of maps into M. And the kind of maps into M are exactly what Kevin was saying yesterday. That these are kind of locally constant maps, which was a notion that makes people unhappy, but we'll try to discuss that. So the idea is that fields, so the fields on X are maps from X to M. And I'm using this kind of funny notation to suggest for maps, this is just maps, but it's a topologist version of maps. The idea is that I'm going to think of X really not as a manifold, which it is, but as a homotopy type. So this notion of map, these are going to be these locally constant maps of Kevin. This is going to be thinking of X as a combinatorial object, as a simplicial set, or if you like, think of it as topological space up to homotopy. This is going to be it's not going to be something like holomorphic maps that appear in the A model. So we're going to think of, so that's what my fields on M are. So what kind of a beast is this? This is going to be an object of derived algebraic geometry. And the idea is that Z of X is going to be some linearization of this space of fields on X, which is this. We already saw an example of that. That was 2D Yang-Mills theory, where M was not a variety, but a stack, was point mod G. So if M is point mod G, the classifying space of G bundles, then essentially the definition is maps from, well, one thing is definition of the other, I don't know which way. Maps from X to M are exactly G local systems on X. So that's the case of gauge theory, or flat G bundles if you prefer. But this is something that really depends on, that's kind of locally constant. The local systems are exactly encoding the fact that this is locally constant maps. This is X is being treated topologically. So that's going to be my, my space of fields. And so now I need to linearize these space of fields. And so let's start, cobordism hypothesis suggests we start with X to be a point. So we're going to make a 2D field theory, so I need to attach a category to a point. Well, maps from a point to M is just M. There we don't have to worry about anything. And we need to linearize, M to get a category. And so let me just look at the category, derived category of coherent sheaves on M.
Why that one?
Why not?
I mean, why not something simply like cohomology?
That's good too. Then I get string topology. I mean, that's my choice of theory, right? There's this. I have this is my space of fields, and my Lagrangian in this kind of setting, or some kind of that's probably the wrong use of the word, but I need to decide how am I linearizing the space of fields, and each time you linearize it in a different way, you'll get a different theory. So you can do that, and that's great. That's a different theory. So the B model means this. Okay. So okay. Now, all right. So now,
Teach me language. What would K theory do?
what?
What would K theory then?
Something else. Yeah, I don't know that I can make that into something that satisfies all the operations I need. But anyway, I need a category, so I'm not, Okay. All right, so this is my, by the way, your example is the same. It's if I really treating an M as a homotopy type, then it's sort of the same, coherent sheaves and modules for cohomology are the same kind of thing.
These are not D modules. These are just coherent sheaves. Right?
These are just coherent sheaves. Yeah, maybe let's drop the D just so it doesn't confuse anyone. I just put it there once to say derived, but I said derived in front of the whole series of talks, so it's derived.
I mean, actually, before you said you can treat X as a homotopy type, M also a homotopy
No,
type?
that's your example is M as a homotopy.
Oh, I see. Okay.
Yeah, here I don't want to treat M as a homotopy type. M is a variety. Okay, so this is the derived category, so it's the differential graded category, and I'm going to be very sloppy and not worry about whether I'm looking coherent, quasi-coherent, various variations. So in a second, it won't matter. Look at DG category of chain complexes of coherent sheaves, sheaves on this variety M. So for example, I have a functor which is global sections, which is maps from the structure sheaf, which goes to R mod, where R is the ring of global functions on M. So you can go from this to modules over a ring, but this is, if M is not affine, this is not a terribly good way to measure this. So we just want to look at this, this category itself in general. So now, okay, now that's what I attached to a point. Now the cobordism hypothesis tells me that this will generate a field theory, at least if this thing is nice enough. And so let me just write the conditions that this category is always going to be one dualizable. So it always defines a field theory on one manifolds, and it's two dualizable, and it's two dualizable if and only if M is smooth and proper, e.g. projective. Okay, so that's the condition, and it's going to be oriented. I'll have an oriented structure in this theory. Oriented structures correspond to Calabi-Yau structures on M. And I'm going to be ignoring dimensions about shifts. So there's some annoyance with gradings, but let me ignore that. Okay.
When you say two dualizable, that's to get like a totally finite theory, but we also discussed this notion of like relativity. So
yeah, I'm not sure the precise condition. Certainly, if it's smooth and proper over this ring of functions, that'll be two dualizable in this weaker sense, and I'm not sure it's any more general than that.
So what if you just have proper and not smooth?
That's
Like clear Hitchison.
you got something else. I don't know.
You get
Yeah.
1.5. You get masking coordinates, but you don't get another.
Okay, so let's look at where the action is going to be here. So let's fields on the circle. So let's describe the circle, the space of fields on the circle. What is it going to be? Well, it's supposed to be maps from S1 to M, which I'm going to call the loop space of M. But it's a loop space in this kind of derived sense. So S1 here is, and M are two different kind of beasts. S1 is a homotopy type, M is a variety. So you ask, what is this loop space of M? Well, this is actually pretty easy to describe because S1, if I'm thinking of S1 combinatorially, I could just draw it, for example, as 2 dots and 2 arrows. So what does it mean to map 2 dots and 2 arrows into M? Well, I have 2 points in M, so that's M cross M. And the 2 points are equal, and they're equal. So that's this simplex, this one simplex is going to be said that these 2 points are identified up to homotopy. Well, there's no notion of homotopy in my variety. This is just going to be interpreted as an equality. So I have 2 points that are equal and are equal, which means that I have 2 points in M that are identified in M cross M. Or maybe a nicer notation for this is the diagonal intersect the diagonal inside of M cross M. So I have 2 points that are identified twice. 2 points identified once as the diagonal, identified again as you're also on the diagonal. So what does this mean? Well, you can calculate this using like Kevin was suggesting yesterday. You can calculate it using a Kazul resolution. And the claim is what this thing is the tangent bundle to X with a shift. So what does this mean? Well, this is certainly not a transverse intersection. It has this kind of, the tangent bundle is recording how non-transverse it's all the excess intersection. So this is kind of, this tangent bundle is reminding you with the shift exactly all the extra directions you need to make this transverse. Let's say this a little more geometrically. What is the, so let's just write it in this. So what is Z of S1? Let me emphasize Z of S1 cross R. So I'm thinking of this as because I'm thinking of the frame theory at this point. So this is, we already discussed this in the 2D theory, in the Yang-Mills case. This is the Hochschild homology of this category, which, and what does that mean? That just means function. So Z of S1 cross R is just going to be functions on LM. That's how I'm going to linearize the space of fields. I want functions, holomorphic functions on the space of fields. And what does that mean? That means it's global sections of functions on M. So that's functions on M. And then I have functions on M. And then I tensor them over functions on M, functions on M cross M, which is OM tensor OM. So I need to calculate this tensor product. Of course, if I'm calculating it in a non-derived way, I just get OM again. But again, emphasize this is a derived tensor product. And this derived tensor product you can calculate using a causal resolution.
Is that xn?
T's of M, not T's of X.
Oh, sorry. Thank you. Yeah, X here is just this circle. So we have, and so you can calculate what this Hochschild homology is, this functions on the loop space. So here this is the global sections of, what is this Tor? It's just the symmetric algebra of differential of one forms on M again, but thought of as in degree -1, which is a notation for just the complex of differential forms on M, except with a kind of negative degree. So it's just differential forms on M, put in a negative, put in kind of homological degree, and we're just taking global cohomology of this, which is just a direct sum of the HPQs of M. It's the cohomologies of differential forms, the coherent cohomologies of differential forms on M. Okay. Again, gamma is, they're secretly, and everything is derived. So this is what these differential forms are. So this is what you attach to the circle. It's just the HPQs on M.
And why is the splitting there?
Which would,
The Hodge splitting.
well, there's no Durand differential. This is just literally the hypercohomology of the complex of differential forms with differential 0. So it's just a direct sum of all the cohomology groups of all these sheaves. There's no Durand differential here. Yeah. Okay, so that's what you attach to the circle. It's just this differential forms. Now, on the other hand, you can also calculate what you attach to the annulus. Well, it's going to be a linearization of the same space, right? Space of maps from the circle doesn't depend on the framing. It's a linearization of the same space of maps from the circle, but it's going to be a different linearization. This is the Hochschild cohomology of this category coherent sheaves on M. And again, I remind you, you look back in your notes, we did all of this in the case of BG for G finite group. There was nothing derived there. This was the center of the group algebra there. And that just means you take global sections instead of a tor of an X. You take X from OM to OM over OM cross M. So it's the same thing as before, just with a different orientation, different framing. And so this gives you the same way you get the global sections of the exterior algebra of the tangent sheaf instead of one forms. Now sitting in cohomological degrees. So you just get, so this is polyvector fields on M. And now if you have a Calabi-Yau structure, if you have a volume form, if you have a holomorphic volume form, you can identify these two by contracting with the volume form. So you could see the lack of dependence on the framing if you give me a volume form. Up to some degree shifts, these two are identified by just contracting with the volume form. And so now what is on the other hand, we said that what you attach to the annulus is an E2 algebra. What is the E2 algebra? Well, this has a graded commutative multiplication, just the wedge, but it also has a bracket, and this is the Schouten-Ninehouse. Let me just write Schouten. The Schouten bracket. There's a bracket on here which is just generated by the Lie bracket on vector fields, but it's become an odd bracket because I've put vector fields in degree 1. So if you think what the bracket is, and the bracket of two vector fields is again in degree 1, so that's a bracket of degree -1. So that matches the grading we had before. So this is a bracket of degree -1 on this thing. So that's my E2 structure.
I didn't understand why we got cohomology there. Shouldn't we just get PQ forms?
This is, which one?
There.
This is PQ forms. I don't know. This is direct sum of HQ of M with coefficients in omega p.
I still don't understand why that thing remembers both the grades.
It doesn't. I just forgot the grading. It's something. It's not the p. It's something that graded like q minus p or p.
Okay.
So it's not the usual grading, but maybe I'm off by a sign. Okay, so that's the structure of Hochschild cohomology. Has this natural E2 bracket, this polyvector. So it's something that's not so mysterious. It's just a bracket of vector fields, but thought of it as a degree 1 structure. Now, while we're at it, we might as well say what you attach to various. So I won't try to define what you attach to closed manifolds, but for example, you can ask what is for the two-sphere. Well, to define the two-sphere, I better be in an oriented setting rather than a frame setting. So I have a volume form. I have a Calabi-Yau thing, and so I can try to attach some kind of integral, some kind of volume. So let me know. This is some kind of volume of M with respect to this holomorphic volume form. Z of the 2 torus, well, that's another thing that's easy to calculate. 2 torus is circle cross circle. So I just take this circle, and crossing with the circle is some kind of dimension. And what is that dimension here? It's just the Euler characteristic. So this is just the Euler characteristic of my HPQs. So it's the graded dimension of this vector space attached to a circle. And if I've done this roughly correctly, we have our first kind of consistency check. There's a slot here. No one can see it. It says S2 cross T2 cross sigma. Before we said in the Yang-Mills, I already wrote here the volume of some Hitchin space. That's what we got from the Yang-Mills-Higgs theory. On the other hand, if here I wrote B model on the Hitchin space, now the B model on the Hitchin space on the 2-sphere, that's also S2 cross T2 cross sigma. And again, I'm getting a volume of the Hitchin space, just sort of to check some kind of consistency of the picture.
So what is
Sorry?
Why do we have to be oriented to?
Well, if I wanted to get the two-sphere is not framed, doesn't have a frame. I mean, it's a trivial. So
Yeah.
this guy I didn't. But for if I want to have a two-sphere, I need to have the and this volume depends on this volume form. Yeah. So okay.
Another question.
Yeah.
So you talked yesterday about how you can break up like the contributions. So I guess here you'd be able to look at these as functions on the loop space.
Right. So, but yeah, that's right. So, but what I'm doing here is I'm taking global functions on the loop space. My ring attached to the circle. It's not I'm not thinking of this sheafified. Just the global. This is my what I.
Yeah.
Well, either one of these, if you want. That's what this ring I attach to the circle. Maybe it's more naturally this guy. Now, when I take spec of this, let me be really lazy and answer your question in a stupid way, which is to say, in degree 0 here, all I have is functions, global functions on M. Right? And then I have some derived thickening of this, which is actually an E2 scheme. It has an odd Poisson bracket. But I say I don't understand odd direction, so basically what I see here is spec that my moduli space, up to some derived stuff, is just the affinization of M. It's spec of global functions on M, and that's usually, but my M was smooth and proper, so I don't actually get anything. So this is, well, you could take a direct, the Yang-Mills picture was a discrete, we had a discrete thing, so you could take a, disconnected variety. You'll see the connected components, but it's not terribly interesting in this case. It will be later, yeah.
Sorry, are you stupid? Which slot was the consistency check for?
S2 T2 sigma.
Okay.
Yeah,
What is this volume?
I don't know.
Like, what's the definition?
I don't know. What is it? Some integral of, I don't know. What can you do with a Calabi-Yau form? You can maybe wedge it with its complex conjugate or something? Is that, Kevin, what is this slot?
You could say that because it's a relative theory, this is not a number, it's an element of a Hilbert space with a three-dimensional theory. That Hilbert space with a three-dimensional theory is like sections of K. The volume form is
A section of K. Okay. All right. There we go. Okay, so let me erase that before anyone asks some more about it. And so now let me just, one more structure that I want to emphasize. It's, we said that if we have an oriented theory, we get not just this E2 action, but this two-disk structure. We have an action, there was a change, there's an action of rotation of the circle. So the action of rotation of the circle here is something very, very nice. Now, if I look at Z of S1 cross R, if I look in the cylinder framing, then this framing is always rotation invariant. The other one I needed to, wasn't. This one is always rotation invariant. So Hochschild homology always carries an action of S1, of the topological space of the homotopy type S1. There's an action of rotation on this. Just because, another way to say it, that this is really a family. This is really a family over the space of circles, over family of vector spaces, over B diff S1. That's the moduli space of circles, but there's B diff S1 is just S1, BS1. This is BS1. That means I basically have a single vector space with an action of S1. That's this monogram. So there's an action of S1 here. And what is this action? Geometrically, it's just saying, this is just saying that if I have this loop space of M, that's some kind of space of maps from a circle to M, well, you could just rotate the circle, right? So there's an action on this loop space of this S1. But now, on the other hand, what is this space? This was just the tangent bundle of M made odd. Just the odd tangent bundle. So what does this circle action devolve to? It becomes something very, very simple. Maybe we could just say it in terms of what are chains on the circle. It's an action of, if you like, the group algebra of the circle. Kind of group algebra of the circle. So the group algebra of this, of the circle, that's chains on S1. And again, everything is rational here over C. So this is just polynomials on some element in degree 1 with square 0. So this is, so there's a single guy, which is given by the fundamental class of the circle. So what does it mean to have an action of this thing? So an action of S1 action on a chain complex is the same thing, maybe cochain complex, is the same thing as a differential eta squared equals 0. An action of S1 on a commutative differential graded algebra on a ring is the same thing as an odd or degree 1 derivation with square 0. So it's a square 0 derivation. So what I want to say is that when you look at this action of S1 on this loop space, by the time you kind of identify it with this odd tangent bundle, all it becomes is a vector field. This space carries a vector field, if you like, it's some kind of Lie algebra of the circle. This guy carries a vector field of degree, an odd vector field with square 0. And so what does that mean? Again, it means a derivation of functions. And this is something that we all know, because functions on this loop space, was just differential forms. So if you want to give a derivation of differential forms, you already know one. There's the Durham differential. So the claim is that this action of S1 on functions on LM is the Durham differential. This is Kahn's realization, probably Figen, Sigen, Kahn. So this is a purely algebraic derivation of the, well, I guess the original one was algebraic too. Anyway, it's a different construction of the Durham differential. It's just the action of S1 on this thing. And so, so you can see the Durham differential on differential forms this way. And so what can you do with that? Well, you can try to pass to Durham cohomology. So how do you see Durham cohomology? Well, I just want to incorporate S1. So I have this vector field on my space. I want to look at things that are invariant under that vector field. That vector field is D. So Durham cohomology is going to be roughly what happens when I look at things that are invariant under this vector field. So I look at, so again, from the point of view of topological field theory, I look at Z of S1, and I'm thinking of it really S1 with this annulus framing. This carries an action of S1. It's something I could do in any field theory. And so I could pass to the invariance. I'm going to calculate the invariance of S1. This is some kind of homotopical notion of invariance. Everything is sort of derived. This thing has a name. It's called negative cyclic homology of M in my case. Okay, that's a name. But one way to say, what does it mean invariance? If you like to write it in an annoying way, it's global sections over BS1 or B diff S1 of my bundle. I have this Z of S1. I have a family of S1s over the space of all S1s, and I'm kind of taking global sections of that family. This is really an annoying way to write saying invariance. The only reason I want to write it this way is to point out that whenever I take S1 invariance in a homotopical setting, I get some extra structure. This is naturally a module for cohomology of BS1, or cochains on BS1, if you like, CP infinity. So this invariant notion carries a natural module structure for a ring, which I'll call polynomials in epsilon, where degree of epsilon is 2. That's a fundamental class of CP1 inside of that. So that's the cohomology of CP infinity. So this ring, so when I take this invariance, how I want to think of it is I'm really naturally getting a family, depending on the new parameter epsilon. A family of degree, a parameter of degree 2. If I set epsilon to 0, it's like you've done nothing. You've done nothing, you just recover Z of S1. And what I want to say is I want to set epsilon equals 1, and I'm going to get Durham cohomology. Okay, so I have this parameter that I've introduced, and I wanted to say when you set epsilon to 1, you're incorporating this Durham differential. You're just looking at adding invariance for this new vector for S1. That's just this Durham differential. Now this statement makes no sense. Why does it not make no sense? Since we've had physics around, we could say because epsilon is a mass. This parameter is a massive parameter. It doesn't make sense. This has dimensions of mass. This has a number. These two things have different dimensions. It doesn't make sense to set epsilon equal to 1. So this is exactly turning on a mass parameter in the sense we saw in Tudor's talk. In this setting, this mass parameter means working equivariantly for the circle. When you work equivariantly for a circle, you're introducing this new mass parameter. It doesn't make sense to set epsilon equals 1. So what can you do? Well, it's a graded parameter. You can notice that if I'd set epsilon to be 13, I would have expected the same answer. Everything is C star invariant under this epsilon. The value of epsilon doesn't matter. So if you'd like, I have a family over this epsilon line. This line is really a degree 2 line. It's a graded line. So at 0, I get just my, a Dolbeau cohomology, or cohomology of differential forms. And so to speak, at 1, I want to say I get Durham cohomology. That doesn't really make sense, but what I can do is I can just invert epsilon. I can look at epsilon non-zero. So it makes sense to just say, well, if I have any place except 0, I know I'm supposed to get Durham cohomology. So let's just invert 0. So let's look at, so what it makes sense to do is take z of S1, take S1 invariance, and I'm going to just invert epsilon. I'm going to look over the cohomology of BS1, and I'll just take epsilon and add epsilon inverse. So that just means restrict away from 0. And what I get is the Durham cohomology of M, except that now it's a module over this ring. So tensor polynomials in C of epsilon, epsilon inverse. This is just tensor over C. But notice that epsilon is degree 2. So what I'm getting is Durham cohomology, and I'm basically making it 2 periodic. I'm tensoring it with polynomials in a variable of degree 2. So this is some 2 periodic. From this vector space, I can't really recover Durham cohomology with its Z grading. I can recover Durham cohomology only with its Z2 grading. But this is exactly Kahn's construction. This is periodic cyclic homology, HP. Periodic cyclic homology is not quite Durham cohomology. It's Durham cohomology made 2 periodic. And that's what you get out of S1 invariance in the loop space. So if you're in the oriented setting, then Hochschild homology and Hochschild cohomology are the same, and you can have said that, well, and you get more structure. You get this BV structure. But in any case, this is the main structure that we see. So in the B model, we've seen there's 2 things. There's this kind of E2 structure on one framing of S1. There's an S1 rotation. The other one, that gives this Durham differential. So we're out of time. So we'll have to do this next time, do everything else next time. And so this is going to become this Nekrasov deformation that was besmirched a couple of times yesterday. So we're going to see how, so we're going to play these games with various spheres. Now we're going to go now to higher dimensions. We'll look at various different spheres and do 2 things. Look at the kind of EN kind of structures we get on them, and look on the new deformation parameters. And that's one thing that's going to make this more interesting, is every time you see a circle here, and there's a lot of circles, we're going to have, at least when we're in the really topological setting, we're going to have a bunch of parameters. Every circle here gets attached an extra epsilon parameter, because I can work equivariantly for rotation of that circle. So that will explain why these slots somehow carry so much information, because they actually depend on several parameters. In particular, in geometric lines, we'll see 2 epsilon parameters for the 2 circles, and that's where we're going to be able to see all the structure of geometric lines. Thanks.
Excuse me? I left my cell phone.
Yes, it's right here. It's right here.
Have it?
Yeah. Question? Yeah.
So I assume I could probably go through these calculations, but can you give me like an a priori reason why in general, for this type of, like when I sort of talk about circle actions, why I should expect to get homology and not like the closed things in a complex?
Sorry?
Sort of naive notion of what's the sort of fixed points of a differential.
Yeah, well, that's what negative cyclic homology is. I mean, negative cyclic homology has, in some degrees, is just, I don't know what, closed differentials, and in higher degrees, it'll have Durham cohomology. So I'm not spelling out what HC is. So if literally the S1 invariance is negative cyclic homology, and that sees closed differential forms in there. But I wanted to get to Durham cohomology, so I'm inverting epsilon.
I see. Okay.
Yeah. I mean, if you like, HC is kind of the Riesz construction on the Hodge filtration on Durham cohomology. Yeah.
So 2 questions, but the second one only makes sense if the answer to the first one is yes. So
No.
in the probably. So in the Hitchens
structure.
Uh-huh.
Is that the same as this like
Yes.
degree? Okay. So is
Well, I would like to say that next time, but
okay.
yeah.
So usually, like, in the sort of traditional context, usually I imagine like the Poisson structure appears because the moduli space of vacua is the space of critical points of some Lagrangian. And is there
It's a different degree. I mean, the degrees of, so let me just say one thing, because it appeared in Kevin's talks and appeared in a lot of talks. There's something important about the degrees here. And let me just say that suppose I have a 3D topological field theory. In particular, it will be Rosansky-Witten theory on the Hitchin space. My local operators are Z of S2. That's going to be my local operators in a three-dimensional field theory. This Z of S2 is an E3 algebra, which means it's a Poisson bracket. It's a Poisson algebra. It has a Poisson bracket of degree -2. So if you're starting with a topological field theory, you see a Poisson manifold, but it's a degree -2 Poisson manifold. Or if you like, a symplectic manifold, the symplectic form naturally has cohomological degree 2. And this is exactly the phenomenon we saw in Kevin's talk. If you start with a symplectic manifold, where you thought of the symplectic form as degree 2, you get confused. The signs, the gradings are all off. And you need to add in this degree 2 parameter to make everything fit. Somehow, what topological field theory wants to tell you is the moduli space of vacuum in a three-dimensional field theory is not a Poisson manifold. It's a graded Poisson manifold where the Poisson bracket is degree -2. And if nature handed you such a thing, you would build a Rosansky-Witten theory or whatever, which is a Z-graded, perfectly nice theory. If you're trying to build one out of a holomorphic symplectic manifold, you have to play games. You have to change the degree of the form. But somehow naturally, so the Hitchin space, it's a cotangent bundle. The symplectic form on the cotangent bundle naturally has degree 2. We don't usually think of it as cohomological degree 2, but has degree 2 for some C-star action. And so we should really think of that as the grading. Physicists don't have a cohomological grading. They have grading. There's lots of U1s in the theory. It's not like one is this kind of, for us somehow mathematicians, the cohomological grading is totally different. In physics, it's just one of the U1s. So the U1 that's acting on the cotangent bundle, you should take seriously. That's the one that's going to become the cohomological grading. And so the Hitchin space is really an E3 manifold. It's a space where the Poisson bracket has degree -2. And that's how it appears as modular space of vacuum in the physics. So, but the thing that you said about critical points of Lagrangian, this is what Kevin was explaining, that's a P0. I mean, that's a different kind of structure, I think. But it's a different grading. Yeah, right.
Do the SO3 fixed points of that TS2 have a
Well, it'll be some, higher cyclic homology. I think these things have been considered, but I couldn't tell you a reference. I mean, but there is a natural action, cyclic, kind of higher Hochschild homologies carry actions of SON. Hochschild homology always carries an action of SON. Hochschild cohomology only does if you're in an oriented setting. And you could always try to take invariance, and that's exactly the relation between an EN algebra and an N disk algebra. And there's an invariant, which is this cyclic homology. Now it'll depend not on one epsilon parameter, but on the cohomology of BSON. So it'll have several parameters, and this, again, is how the Nekrasov story will appear for BSO4. There you have, which is kind of polynomials in two variables, which is this Nekrasov epsilon 1 and epsilon 2.
Why does epsilon have dimensions and mass?
I don't know what mass is. What is mass? I don't know what dimensions are, but it transforms in a non-trivial grading with respect to a C-star action. I'm pretending that C-star is related to the renormalization group. I mean, it has some dimensions of something. It's a graded parameter. With respect to the natural U1, there's a natural C-star GM U1 action on everything here, which I'm keeping track of. It has dimensions of whatever. It's a degree 2 with respect to that C-star. And in these examples, somehow this matches with exactly mass parameters.
So did like data from the transit S1 have dimensions of mass of 1/2?
It has some dimensions of something. As graded, I don't know what mass the one, I don't want, I'm making that dictionary too precise. But the dictionary is very, very helpful because you can tell, equivariant cohomology has the same phenomena as the kind of things that Tudor was saying exactly match up with localization theorems in equivariant cohomology. You can think of going to equivariant parameter to 0 is one kind of deformation. Taking the equivariant parameter very large is this kind of where you see equivariant localization. So it behaves exactly like a mass parameter, and in all these examples, the mass parameters that appeared in Tudor's talks and Andy's talks are of this form. They can be interpreted in the topological setting. I don't know anything about non-topological. In the topological setting, those mass parameters are equivariant cohomology parameters.
So I might take the mistaken view that you explained to me in a very confusing way what is Hodge theory. Some aspects of Hodge theory.
Yes.
Can you explain in a similar way the non-abelian Hodge theory?
Yeah, I mean, this is, there's nothing particularly abelian here except my choice of linearization. Right? I mean, you could, in fact, I'll say a version of that next time. You can see if you like, you do this one level up, you do this for categories rather than for vector spaces, you can see something like the category of D modules with its Hodge filtration appearing in the exact same, in Rosansky wind theory on the circle, you literally do the Rosansky wind theory on the circle with this S1 equivariant deformation. It'll exactly give you the Hodge filtration on the category of D modules, which you like is the Hodge filtration on spaces of local systems. So it is the non-abelian Hodge. So you see the non-abelian Hodge, it's in that chart.
Thank you.
Thanks.